Swayam Prabha. Digital India. Educated India.
So, this is the multi-layered feed-forward network, and supposing that we have passed say one set of training scenarios here. Now, if I pass one set of training scenarios and we have discussed like how to get this calculated output, and we have seen how to determine this particular the error of the kth output neuron. Now, based on this particular error, so this error has to be propagated back. So, I will have to update this particular Wjk, and here we have got the connecting weight say Vij. Now, let us see how to update. Now, to update that, actually what we do is to update this Wjk. So, what we do? So, from here we try to move in the backward direction, and the moment it reaches here we will stop. Now, here to update this Vij, so starting from this particular error, so I will propagate it back, and the moment it reaches here I am going to stop. And another thing I am just going to tell you that this particular Wjk has got some contribution on the output of this particular the kth neuron, but it has got no contribution towards the output of the other output neurons. So, Wjk has got contributions towards the output of only this kth output neuron. That means, if I want to update this Wjk, I will have to consider only the kth output neuron and its error. On the other hand, if I want to update this particular Vij, so depending on the Vij, so I will be getting some output here. Now, this particular Hoj has got at least some contribution of this particular the Vij, and here. So, this Hoj is connected to all the output neurons. So, whatever outputs we are getting at the different neurons of the output layer, so this particular Vij has got at least some contribution. That means, if I want to update this particular Vij, so I will have to consider the average error of these particular the output neuron. On the other hand, if I want to update only Wjk, so I will have to consider the error of only this kth output neuron. So, I think I am clear. Now, with this particular understanding, so let me start with the principle of the incremental training, and let us see how to use the principle of incremental training, the principle of which I have already discussed in details. Now, I am just going to discuss how to update. So, this particular Wjk. Now, Wjk is nothing but the connecting weight between the jth hidden neuron and the kth output neuron. Now, this Wjk updated is nothing but Wjk previous plus delta Wjk. Now, this delta Wjk is nothing but minus eta multiplied by, so partial derivative of Ek with respect to your Wjk. Now, let us see how to determine. So, this particular partial differentiation, that is your del Ek del Wjk. Now, this del Ek del Wjk is nothing but del Ek del Ook. That means, the rate of change of Ek with respect to your Ook multiplied by partial derivative of Ook with respect to Oik multiplied by the partial derivative of Oik with respect to your Wjk. So, we are going to use actually the chain rule of differentiation. So, the chain rule of differentiation we are going to use just to find out what should be this particular partial differentiation of Ek with respect to your w j k. Now, here, so this E k is nothing but is your half T O k minus O O k square. Now, if I try to find out the partial derivative of this particular O O k, so I will be getting actually del E k del O O k is nothing but your 2 multiplied by half multiplied by minus 1, then comes your T O k minus O O k. So, this 2 gets cancelled. So, this is nothing but T O k minus O O k. So, this is O O k. So, this is the way actually we can find out. So, this partial derivative is nothing but minus T O O k minus O O k. So, this is the way actually this first partial derivative we can find out. Now, we will have to find out the partial derivative of O O k with respect to your O I k, and if you remember actually on the output layer we use actually your the tan sigmoid transfer function. Now, if you use tan sigmoid transfer function, so very easily you can find out what should be the derivative. Now, let me concentrate on how to find out the derivative of this particular the tan sigmoid transfer function. Now, if you just write down the expression like your y equals to, say e raised to the power say a 2 x minus e raised to the power minus a 2 x divided by e raised to the power a 2 x plus e raised to the power minus a 2 x. Now, if you find out the derivative, that is dy dx, so you will be getting this particular expression, that is nothing but a 2 multiplied by 1 plus y multiplied by 1 minus y. So, we can find out this particular derivative, and all of us we know how to find out the derivative with respect to x, and if you simplify, so you will be getting this particular the expression where y is nothing but, so this particular the expression. The same thing we have copied it here just to find out the partial derivative of O O k with respect to O I k is nothing but a 2 multiplied by 1 plus O O k multiplied by 1 minus O O k. So, very easily you can find out, so this particular the partial derivative. Now, then comes your the partial derivative of O I k with respect to your w j k. Now, here if you remember, so this O I k is what? That is nothing but the input of the kth neuron lying on the output layer, and if you just find out that particular expression, that is your O I k, there will be a few terms, and in fact, there will be a few terms, but at the middle almost we will be getting a term, that is nothing but H O j multiplied by your w j k, and there are a few other terms. Now, what is this? This is nothing but the output of the jth neuron lying on the hidden layer multiplied by the connecting weight, that is your w j k. Now, if I find out the partial derivative of O I k with respect to your w j k, so definitely I will be getting, so this particular H O j. So, very easily we can find out all the derivatives, and once you have got all the derivatives, now we are in a position to determine what is del E k del w j k. So, we substitute all the values, all the expressions, then we will be getting, so this particular the final expression. And once we have got this particular final expression of the partial derivative, so we can find out delta w j k is minus eta into this particular partial derivative. So, I will be getting eta a 2 T O k minus O O k 1 plus O O k 1 minus O O k multiplied by H O j. So, very easily we can find out what should be. So, this particular the change in W. Now, once you have got the change in W, Now, we are going to discuss like your how to find out the change in V matrix. Now, let me concentrate on Vij, that is nothing but the connecting weight between the ith input neuron and jth hidden neuron. So, Vij updated. So, Vij updated is nothing but your Vij previous plus delta Vij, and I have already discussed that this particular delta Vij, if I want to determine. So, we will have to consider the average effect. AV stands for average. So, it is nothing but minus eta partial derivative of E with respect to Vij average. Now, how to find out this particular expression? Del E del Vij average is nothing but summation k equals to 1 to p. In fact, this should be your capital P, the notations which you are using. So, partial your summation k equals to 1 to p. So, partial derivative of E k with respect to your Vij multiplied by 1 divided by p. Now, once you have got this particular expression, now we will see how to determine in fact your this del E k del Vij. Once again we are going to use the chain rule of differentiation, and this is nothing but is your. So, partial derivative of E k with respect to O OK, that means the output of the output neuron multiplied by the partial derivative of O OK with respect to O I k multiplied by the partial derivative of O I k with respect to H O j multiplied by the partial derivative of H O j with respect to H I j multiplied by partial derivative of H I j with respect to your V I j. Now, we have already discussed how to determine. So, these partial derivatives, that is partial derivative of E k with respect to O OK, that is nothing but this particular expression. We have also seen how to determine this particular expression of partial derivative, and that is nothing but this particular expression. And now, I am just going to discuss. So, how to find out the next one, that is del O I k del H O j, that is the partial derivative of O k with respect to H O j, that is nothing but W j k, that also we have seen. Now, I am just going to find out the partial derivative of H O j with respect to your H I j, that means your this is the jth output of jth neuron lying on the hidden layer, and this is the input of jth neuron lying in the hidden layer. Now, in the hidden layer actually we have used one log sigmoid transfer function, which is nothing but 1 divided by e raised to the power minus a 1 x, and if you find out its derivative, that is dy dx. So, this will become your a 1, then comes y multiplied by 1 minus y, this you can check. And once you have got this particular expression, so very easily you can find out the partial derivative of H O j with respect to H I j is nothing but a 1 H O j multiplied by 1 minus H O j, and the last term, that is your partial derivative of H I j with respect to V I j, that is nothing but I O I, that is output of the ith neuron lying in the input layer, and this is nothing but the input of the ith neuron lying in the input layer. So, I can find out this particular expression, and once you have got it, now we can find out what is partial derivative of E k with respect to V I j, and this is nothing but. So, this particular the big expression, and once you have got it, now we can also find out actually what should be your this particular V I j. Now, V I j is in fact nothing but your. So, this particular expression. So, this is your this V I j del E del V I j average is nothing but this, and we have already discussed how to determine this particular thing, and once we know this I can find out this average, and once I know this average I can multiply by eta and put one negative sign, that is nothing but is your change in Vij. So, we are in a position using this particular your differential calculus just to find out what should be the change in connecting weights or the updated values for this particular the connecting weights using the incremental mode of training. Now, I am just going to discuss the batch mode of training. Now, this batch mode of training, the principle I have already discussed, that supposing that I have got a large number of training scenarios, say capital L number of training scenario. Now, if I have got capital L number of training scenarios, so what I do is we pass all the training scenarios one after another and we try to find out what is the error corresponding to the each of the training scenarios. We try to find out how much is the total error. We also try to calculate what is the average error, and based on this particular average error we update the network only once. Now, let us see how to implement this. Now, let us consider that there are capital L number of training scenarios. So, mean squared deviation in prediction for the kth output neuron, that can be written as, that is E prime is half multiplied by 1 by L and we will here we will have to consider the summation. So, multiplied by summation L equals to 1 to capital L T O K L minus O O K L square. And here actually what we will have to do is, once again we will have to update the W j k and V I j, that is the connecting weight between your the hidden neuron and output neuron, and that between the input and the hidden neuron. Now, let us see how to update this particular your the W j k. Now, this delta W j k is nothing but minus eta multiplied by partial derivative of E prime with respect to your W j k. Now, how to determine this particular partial derivative? To determine the partial derivative, so I am once again using the chain rule of differentiation. So, this del E prime del W j k is nothing but del E prime del E L, that means the error corresponding to the small lth training scenario. Then comes the rate of change of E L with respect to your E k, then comes your the partial derivative of E k with respect to O O k, partial derivative of O k with respect to O I k, partial derivative of O I k with respect to your W j k. Now, here I just want to mention one thing. Now, regarding the last three terms, for example, these three terms we can find out some numerical values. Okay, like if we assign some numerical values, so ultimately you will be getting some numerical values. But the first two term, that means your this particular partial derivative and this particular partial derivative, it indicates only the rate of change of E prime with respect to the lth training scenario and the rate of change of error with respect to the lth scenario with respect to your the E k, that is the error of the kth output neuron. So, these two things these two partial derivative actually are used just to tell you that we will have to sum all such things up, we will have to sum them up, but you may not get the direct numerical value corresponding to this first term and this particular the second term. But starting from the third up to the fifth term, you will be getting some numerical value. Now, this is the way actually you will have to find out the partial derivative of E prime with respect to your the W j k. Now, then comes here how to update the V I j. Now, this delta V I j is nothing but minus eta, the partial derivative of E prime with respect to V I j average, and this particular del E prime del V I j average is nothing but summation k equals to 1 to p capital P del E k prime del V I j, and we will have to sum them up and then we will have to multiply it by 1 divided by capital P. So, this is the way actually we can find out the average of this particular the partial derivative. And how to find out this, like del E k prime del V I j. So, this del E k prime del V I j is nothing but del E k prime del E k L multiplied by del E k L with respect to your del O O k. Then comes your partial derivative of O O k with respect to O I k, partial derivative of O I k with respect to H O j, partial derivative of H O j with respect to H I j, partial derivative of H I j with respect to your V I j. Now, we have already discussed like how to find out these derivatives, and I can also find out the numerical values corresponding to each of the partial derivatives. But once again, so the first this particular component, that is the partial derivative of E k prime with respect to your E k L, you may not be able to determine the numerical value, but it indicates the rate of change of E k prime with respect to E k L. Similarly, this is nothing but your the rate of change of E k L with respect to your O O k. Now, these two terms is going to help us or going to tell us that you find out. So, this particular expression for each of the training scenarios and you sum them up just to find out the total effect, and so that we can find out the average effect for updating of that particular the connecting weights. Now, once you have got this particular derivative using this particular formula, so I can find out this average, and once I have got this particular average, so I will be able to find out what should be the change in V I j. So, this is the way actually we can update the connecting weights using actually the batch mode of training. Now, supposing that we know the updated values for this particular the connecting weights. Now, if you see this particular the rule, now let me just write it here. For example, say the change in W is nothing but, let me repeat. So, minus eta multiplied by partial derivative of error with respect to your W. Now, if I follow this particular rule, that is called the delta rule. Now, there is a possibility. So, this particular partial derivative, it could be either positive or negative, but this eta is always positive and it is lying in the range of 0 to 1. Now, this eta is positive, but this partial derivative could be either positive or negative. Now, supposing that it has become negative, and here I have got another negative sign. So, that will make the delta W is actually a positive value in some of the iterations. Now, that means while updating this particular W, if I just go on adding some numerical value, so after running this particular algorithm for a large number of iteration, there is a possibility that the value for the W may come out of the range. For example, the range is 0.0 to 1.0, another range could be minus 1.0 to plus 1.0. Now, if I just go on adding, so this particular updated value, then what will happen actually or, so this weight may go out of the range and the network may lose the stability or the balance. Now, neural network actually does not know anything of the physical problem. So, if it is wrongly trained, then also it is going to give some results, but we will have to be careful that the stability of this particular network should be maintained. That means, your W should not exceed its own range. Now, supposing that W is found to be so greater than 1, in that case So, we will have to use some correction, and that correction is something like this. So, what I will have to do is, if w is found to be greater than 1, so I am just going to put 1 w by 1 divided by w. Now, if I consider 1 divided by w, this will become less than 1, and once again I can train this particular network for more iteration. The moment I put 1 divided by w in place of w, there could be a sudden change in the performance of the network, but after a few iteration. So, once again it is going to reach that particular the balanced region, and this particular network can be believed only if it is working in that particular the balanced region. Now, to overcome this particular problem, so that w does not become greater than 1. So, what I do is, we use the generalized delta rule, and that is nothing but is your delta w t, t indicates tth iteration, is nothing but minus eta multiplied by the partial derivative of E with respect to w corresponding to the tth iteration, plus alpha prime multiplied by delta w t minus 1. So, this particular extra term we are going to add, and alpha prime is known as the momentum constant, and the range for the momentum constant is once again from 0 to 1. And what I do is, we try to see what was the change of w in the previous iteration, that is nothing but t minus 1th iteration. That means, we try to see the history of this particular the updating. That means, what happens at t minus 1th iteration to this particular delta w, that I am going to consider. Now, if I consider that, then there is a chance that I am going to provide some sort of damping effect to this particular network, or I am just going to put some sort of cushioning effect to this particular the network, and so that the w does not exceed its range. But if I follow this, once again there is no guarantee that if the network is running for a large number of iterations, so it may once again go out of this particular the range, and if it goes out of the range, so this is actually the remedy. Now, as I told, that just to put some sort of damping effect to this particular network, we consider its history. That means, what happens to the previous iteration, we want to give some weightage to this particular the change in connecting weight, just to find out what should be the updated weight. So, this is the way we can update so this particular the network. Now, a few notes here I have put. So, I just want to mention. Now, this multi-layered feed forward network trained with the help of this back propagation algorithm, that is the delta rule or the generalized delta rule, there is a possibility that there will be a local minima problem. The reason is very simple, because it works based on the steepest descent algorithm, and that means it is going to use the information of the gradient. Now, supposing that, say I have a very complicated error function with so many such ups and downs and undulations. Now, what I do is, while minimizing the error, so this particular algorithm will try to find out the search direction which is opposite to the gradient. Now, gradient is a local property. So, there is a chance that it is going to get stuck at the local minima, and it will not be able to reach that particular your globally optimal solution. And this back propagation algorithm is actually it is having a chance of local minima, and the transfer function has to be differentiable, because we are using the gradient information, and at the point of discontinuity, in fact, we are we will not be able to find out the gradient of these particular the objective function or the error function. Now, this back propagation neural network or multilayered feed forward network trained using the principle of back propagation algorithm may not be able to capture the dynamics of a highly complex or highly dynamic process, and that is why actually we will have to go for some feedback circuit, which I will be discussing in details. That means, we will have to go for the recurrent network. Those things will be discussed in much more details while discussing the recurrent networks. Inputs are to be normalized, I have already mentioned. The range for the connecting weights I have already mentioned, and actually we will have to find out some convergence criteria for this particular the algorithm during the training. Now, if the rate of change of error in prediction becomes less than or equal to some pre-specified small value, we say that that network has reached that particular optimal situation, and we consider that particular network as the optimal network. Now, a neural network could be either a fully connected network or it could be a partially connected network. Now, very quickly let me take a very simple example. So, if I have got say one network having this type of structure. So, it is 2 input neuron, 3 hidden neuron and 1 output neuron, and if the connectivity is something like this, all the neurons are connected. So, this type of network is known as the fully connected network. On the other hand, if I have got a network of this type, like if I have got a network of this type, say I have got these are the input neurons, and supposing that these are the hidden neurons and this is the output neuron, and if the connectivity is something like this, if the connectivity is something like this, so this is nothing but actually one partially connected network, because this connectivity is actually not ensured. Then comes your this connectivity is not ensured. So, dotted lines are actually absent. So, this type of network is known as the partially connected network. Thank you.